Welcome back. In this video I'll be explaining to you the naive Bayes classifier, how it works, and we'll take a simple example. Now the naive Bayes classifier, as we mentioned before, is based on the frequency table. Naive Bayes classifier is based on Bayes theorem with independence assumptions between predictors. I hope you're familiar with Bayes theorem. It's very nice and easy and quite a nice way of explaining how things work. And we assume that our predictors are independent. What that means is knowing the value of one attribute does not tell us anything about the value of another attribute or another predictor. A naive Bayes model is usually easy to build with no complicated iterative parameter estimation, and that makes it particularly useful for very large data sets. So naive Bayes is quite well known and well liked amongst the research community. It's quite simple, but it actually performs really well quite often. Even sometimes it outperforms sophisticated methods. The good thing about naive Bayes classifier is that it's easy to understand and easy to explain and easy to debug. Now the way it works, as we mentioned before, it's based on Bayes theorem. Bayes theorem provides a way of calculating the posterior probability of C given X. C is our class, X is our data or our predictors or our attributes, from the probability of C, probability of the class, that's before seeing any data, probability of the data, and probability of the data given the class. Naive Bayes classifier assumes that the effect of the value of a predictor X on a given class C is independent of the values of other predictors. So predictors are independent from each other. This assumption is called the class conditional independence. Now let's have a look at this equation here. Probability, this is red, probability of C given X, probability of the class given X. X here is our data or our predictors. We can have one or more predictors, yes? Probability of the class given the data equals probability of the data given the class times probability of the class, this is probability of the class before seeing any data, divide by probability of X, i.e. probability of the data itself. This is called the posterior probability, probability of C given X. Probability of X given C is called the likelihood. Probability of the class is called the class prior probability. Again, this is the probability of the class before seeing any data. And here probability of the data is called the predictor prior probability. So probability of C given X is posterior probability of class or the target given predictor or attribute. C given X, X is our attribute. Probability of C is the prior probability of the class. Prior means before seeing any data. Probability of the data given the class is the likelihood, which is the probability of the predictor given the class, and probability of X is the prior probability of the predictor, probability of the data itself. Sometimes it's not always possible to know probability of X, this one here, but there's a way around that. So the probability of C given X, which is X is our attribute, is the probability of the first attribute given the class times probability of the second attribute given the class times, and we go over all the n attributes that we have given the class times probability of the class itself. The reason we multiply probabilities here is because, as we mentioned before, the predictors are independent. So this independence assumption helps us to solve this by multiplying probabilities. Let's take an example. The posterior probability can be calculated first by constructing a frequency table for each attribute against the target. So we do frequency tables, remember? If our data is numerical, then we can transform it into categorical, or I'll show you another technique in the next video, how to deal with numerical variables to build a Bayesian naive Bayesian classifier. Now, after we build the frequency tables, we transform them into likelihood tables or into probability tables, and finally we use the naive Bayes equation to calculate the posterior probability for each class. Now, the class with the highest posterior probability is the outcome of prediction. Let's have a look at an example. If you remember the weather data now, for example, we have 4 categorical attributes and we have our class. What we do here is, for example, we calculate the probability of the class. Now this is the prior probability. Probability of yes is 9 over 14. Probability of no is 5 over 14, yes? And now we build a frequency table. You've seen this before in the 1R classifier. And from the frequency table, now from these counts, from the frequencies, we extract these probabilities. Probability of yes given it's a sunny. I'm sorry, probability of sunny given it's a yes, probability of sunny given it's a no, probability of overcast given a yes, and so on and so forth. And these are just the frequency over the sum of the column. So 3 over 9, 4 over 9, 2 over 9. This column here sums to 9 because we have 9 yeses. And here 2 over 5, 0 over 5, and 3 over 5 because this column here sums to 5. We have 5 nodes, yes? Likewise for the two different values for humidity, high and normal, we compute their corresponding probabilities. Likewise for windy and for temperature. If you see here, for example, for the outlook, we have the frequency table and we have the probabilities now. Now, if we see here, the probability of x given c, so probability of the variable given the class, is read as follows, or extracted as follows. Probability, for example, probability of sunny given yes, of sunny given the class is yes, is 3 over 9, or 0.33. The probability of sunny given it's a no is 2 over 5. Yes? And now, the probability of just sunny regardless of the class, this is the probability of x, is 5 over 14. Probability of overcast is 4 over 14, and we continue likewise for rainy. And now at the bottom here we have the probability of yes and the probability of no. As we mentioned, this should sum up to 9 and this should sum up to 5, the number of yeses and the number of no's. I hope this makes sense. Now let's say, for example, we want to compute the probability of yes given the day is sunny. So what we do is we multiply probability of, and this is, by the way, probability of c given x, so we have probability of x given c, we multiply probability of sunny given yes, which is 3 over 9, times probability of c, which is yes, now our class is c, which is 0.64, and we divide by the probability of x. The probability of x of sunny now is 5 over 14, which is 0.36, and that results in 0.6. Yes, just a direct application of this equation here, and we mentioned that probabilities multiply because we have independence. Now for these we can use a simple example, for example, from this table. Let's say we have a random day now, some input. Now we want to decide either to play or not, yes or no. Let's say we have a day with outlook rainy, temperature mild, humidity normal, and windy is true, and we want to decide either to play or no, or either to play or not using naive Bayes classifier. What we do is we compute the likelihood of yes and the likelihood of the no. So the probability or the likelihood of the yes is the probability of the outlook equals rainy given it's a yes, times probability of temperature mild given it's a yes, times the probability of humidity is normal given it's a yes, times the probability of the windy is true given it's a yes, times the probability of yes. And these values we can extract them easily from our frequency and probability tables, as you can see here. So for example, probability of outlook equals rainy given it's a yes is rainy given it's a yes, it's actually 2 over 9, yes. Likewise, probability of temperature is mild given it's a yes is probability of temperature is mild given it's a yes, it's 4 over 9, and we multiply these things together and multiply by the probability of the yes, which is 9 over 14, and we get this number. This number now is not a probability, it's just the likelihood of the yes, because in the same way we can compute the likelihood of the no. Probability of outlook is rainy given it's a no, probability of temperature is mild given it's a no, likewise humidity normal, windy normal given it's a no, times the probability of the no, and we can extract these from the table. For example, the probability of windy is true given it's a no, probability of windy is true given it's a no is 3 over 5, and that's, as you can see there, times 5 over 14, which is probability of the no, and we get that. Now we can normalize to get the probability. For probability of yes is likelihood of yes over likelihood of yes plus likelihood of no, we get probability of yes. Probability of no is likelihood of no over likelihood of yes plus likelihood of no, and gives us that probability. And notice now that probability of the yes is larger than probability of the no, so we'll probably decide to play on that day. This is how the naive Bayes classifier works. You may have noticed something, because we multiply probabilities. If we have zero frequencies, then we have a problem. If you remember this idea of independence, and we multiply probabilities, if we have zero counts, if we have zero counts, then we have a problem, because we multiply by zero, we end up with a zero for that value. Well, there's a way around this, and this is called the zero frequency problem. It happens when an attribute value, for example, outlook is overcast, doesn't occur with every class value. For example, with play golf equals no. So here, if you see the outlook is overcast and play no is zero, it doesn't occur, and that causes a problem. And the way around that is to add 1 to all the counts. We just add 1 to all the counts. So these counts, instead of 3, 4, 2, 2, 0, 3, they become 4, 5, 3, 3, 1, 4, and we do the same thing for everything else, and this probability will slightly change, but that's just a way around this zero frequency problem. Thanks for watching. In the next video, I'll show you how to deal with numerical data when trying to build a naive Bayesian classifier.